Good day, class. I'm sorry I can't be with you today. I'm off at a school meeting at another school actually for a few days. I hope that you enjoyed your week away. We will go over the test at some time in the very near future. But in the meantime, I've got this brief video to try and help us continue moving on. So if you would, open up your notes to 10.08. That's where we'll be at today. And our goal is to use what we've done. I know what we've done has been very challenging to you, but this next part I believe is a little bit easier because we're going to go ahead and assume some certain things already, so it'll be a little bit easier on you, I think. But our goal is to be able to approximate the function value of a transcendental function with an elementary function. Now, what do we mean by transcendental function and elementary function? If you'll look at this graph here, the blue is the sign of x, and you can probably recognize that. That is called a transcendental function, so an example would be the sign of x. An elementary function is one that is considered to be a polynomial. So it might be 1/6 x cubed plus 3/4 x squared, blah, 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 blah. Anything that is like that is considered an elementary function. So as we look at this, you see that the red line is an elementary function, and you see that it does seem to match the sine function at certain places. Now I can change that function, that red function, to a different function, and it will show up and match up in a few more places than what that does. Notice that when you look at it here, that looks like probably a cubic function, and it matches in more places. And if we go to something that's to the fifth order, it matches in more places. So that's what our goal is. How can we take a function like the sine of x and approximate it using a polynomial function like this? The reasons for that we'll get into later, but it is an important concept to be concerned with. And instead of going through how we came about this, we're going to skip over that for time's sake. And these are two very special polynomial functions that will approximate certain transcendental functions. This is called a Taylor polynomial or a maclaurin polynomial. They're really the very same. The only difference is where they are centered at. So what the Taylor polynomial says, you can write a polynomial based on the function value at a certain number plus the derivative at that function value times x minus c plus the second derivative at that function value over 2 factorial times x minus c squared, and so forth and so on. It'd be the third derivative over 3 factorial times x minus c cubed. If you can write that polynomial out, something that looks like this, this is called a Taylor polynomial, and it's said to be centered at C. So C would be something that you already know. So for example, with the sine function, you would probably center it at 0, or you would center it at pi over 4, or you would center it at pi over 2, somewhere that you know the value of that particular function. You wouldn't start at the sine of 28 because you don't know what the sine of 28 is. You might start at the sine of 30 degrees because you know what the sine of 30 degrees is. So that's what a Taylor polynomial is. And if you look right below it, a Maclaurin polynomial is very similar. The only difference is this one is centered at 0. So it's really just a simplified version of a Taylor polynomial. A Maclaurin polynomial, if you see that word, you know that it's centered at 0. But it's the same thing. It's the function value plus the derivative times x plus the second derivative over 2 factorial times x squared plus the third derivative at 0 over 3 factorial times x cubed, and so forth and so on. So we're going to try to take this and use that information to figure out an approximation to the natural log of a function. Now, the natural log, you'll notice in what's written here, it says P0, P1, P2, P3, P4. Well, what we're looking for that means polynomial of degree 1. So we're just going to use the function value for it. P1 would have the first derivative, P2 would be the second derivative, P3 would be the third derivative, P4 would be the fourth derivative, and so forth and so on. So if we're going to start this off, notice that it's centered at 1, at c equals 1, so that's going to be a Taylor polynomial. We're going to start this off by writing down what is f of x, or f of x is the natural log of x. Well, what is the derivative of natural log? We studied this way back in October. It's 1 over x. And then we're just going to continue taking the derivative. We need up to the fourth derivative, so we'll take the first 4 derivatives here. What's the derivative of 1 over x? Well, 1 over x is the same as x to the negative 1, so the derivative is negative 1 times x to the negative 2, which is negative 1 over x squared. And then the third derivative, well, again, if we use our power rule, negative 1 times negative 2 makes that a 2 times x to the negative 3, so we get 2 over x cubed. And finally, the fourth derivative will be 2 times negative 3, which is negative 6 x to the negative 4, which is negative 6 over x to the fourth. And oftentimes we can see a pattern to these. We're not going to worry about that pattern right now, but we're just going to leave it just like that. Well, we need to know those function values and those derivatives, but we also need to know those function values at 1 because we're centered at 1. Well, the natural log at 1 is 0. The first derivative, when we put 1 into it, we get 1. When we put 1 into the second derivative, it's negative 1. The third one is positive 2. The fourth one is negative 6 because x to any power is going to be 1. So that's what our function values are going to look like. Now if you'll go back and look and see what is a Taylor polynomial, I'm going to take this graphic here and copy it down here so we can utilize it. So if we're looking to find a Taylor polynomial, those are our function values up there. So I'm going to go ahead and write out the first one. P of 0 is just going to be the function value at 0, which is 0. Then the first degree polynomial is going to be the previous one plus the first derivative, which we said was 1, times x minus 1. The P2 would be the same as P1 plus, now we're using the second derivative. Notice I'm looking at this right here, the second derivative, which is negative 1 over 2 factorial times x minus 1 cubed. Why are we putting 1 in for c? Because we're centered at 1. And if we use P3, it's the same as P2 times, and then we add the next term, which would be the third derivative. The third derivative is 2, so I don't need to write an equal sign there. The third derivative is 2 over 3 factorial times x minus 1 to the third power. I actually made a mistake here when we're dealing with the second one. It's P2 is x minus 1 quantity squared. And then P4 is going to be the same as P3, so I'm not going to write it down, plus negative 6 over 4 factorial times x minus 1 raised to the fourth. And if you look at that polynomial, that is the Taylor polynomial for the natural log of x. So I'm going to write down right here, I'm going to write down the entire polynomial. It's going to be 0, which I'm just going to leave off, 1 times x minus 1 minus 1 over 2 times x minus 1 squared plus 2 over 6 times x minus 1 cubed minus 6 over 24 times x minus 1 to the fourth. And if you were to graph on Desmos, if you were to graph the natural log at x and this polynomial, you would find that they match at quite a few points around the number 1. Now what you'll also find is the further you get away from 1, the more these do not match with one another. So I invite you to try that on Desmos just to show that that actually does work. Okay, so what I want you to do now is I want you to go to the next page, the cosine, and I'm going to put this on the board for you like this. I want you to pause the video, and I want you to see if you can write out the Maclaurin polynomial, P0, P2, P4, and P6 for cosine of x. And then we'll use the P6 to approximate cosine at point 1. So if you would, just pause the video at this point in time, take about 3 minutes, see if you can come up with this. You'll want to do the same thing we did before. You'll want to write down what f of x is. F of x is starting off as cosine of x. Then write out the first 6 derivatives. You might see a pattern to that. Then you'll want to find out what those derivatives are equal to at x equals 0. Since it's a Maclaurin, we know that we are centered about 0. And then you'll want to write out those polynomials. So do that, then come back to the video. So as you can see, I've written out the function and the first 6 derivatives here on the left. And as you notice, there is a pattern. It's cosine minus sine, negative cosine, sine, and then the pattern starts over. So you could easily write out all of as many derivatives that you wanted because you see it's a pattern. They run in a sequence of 4 and then it repeats that. Then when you evaluate it at 0, you see another pattern. The cosine is 1 at 0, but the sine is always 0, so you're going to have a pattern of 1, 0, negative 1, 0, 1, 0, negative 1. It's going to be 0 again. So you've got a sequence there, or a pattern to them that's easily reproducible without even taking any more derivatives. So now if we start off to write the polynomial out, then it said to write out 2, 4, and 6. I'm just going to go ahead and write out the 6th one because I think you can see that it's going to be just a building on each one. So if we are writing out the 6th polynomial, we're starting off with the function value at 0, which is 1, plus the first derivative, which is 0, times x, plus the next derivative, which is negative 1, times x squared over 2 factorial, plus the next derivative, which is 0, times x cubed over 3 factorial, plus the 4th derivative, which is 1, times x to the 4th over 4 factorial. And suddenly you're probably seeing a pattern to this. The 5th derivative is 0 times x to the 5th over 5 factorial. And the 6th would be negative 1 x to the 6th over 6 factorial. So I bet even though we've only written out the first 6, it would be easy for you to write out the first 10 there. I'm going to simplify this a little bit, and all the zeros I'm going to get rid of. So I'll have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And that is our 6th degree polynomial for cosine. So you can see that it's very easy now. I bet you could tell me what the next term, what the 8th degree polynomial is going to be. The 7th is going to be the same as that, so it wouldn't be of any interest to us. So now if you go through and look at that, it's easy, and you also see that our denominator is getting larger and larger each time. Well, we were asked not only to find it, but then to approximate cosine at point 1. So we can say that the cosine at point 1 is approximately 1 minus 0.1 squared over 2 plus 0.1 to the 4th over 4 factorial is 24 minus 0.1 to the 6 over 720. That's what 6 factorial is. And if you work that out on your calculator, you'll get a number. I invite you to go ahead and work it out on your calculator. And when you work this out on your calculator, I get 0.995004163. That's as many decimals as my calculator shows. And then if you also use try to use your calculator to get the cosine of 0.1, I got that to agree to all of those decimal places. So it is a pretty good approximation to what the cosine at 0.1 is. Now I'd like you to stop the video and do this particular problem. It's very similar. I want you to find the third degree Taylor polynomial for sine of x expanded about c equals 0.6. So we're going to once again be able to use 0.6 is going to be a Taylor polynomial. Pi over 6 is going to be a Taylor polynomial. And we're only going to the third, so you're just going to need to know f of x, f prime at x, f double prime at x, and then f triple prime at x. And again, you'll see a pattern to it. So do that. Pause the video, see what you come up with for that. Okay, if you look now, I found the four functions that we need, the function and its first three derivatives. I found the values, 1/2 root 3 over 2, negative 1/2, and negative root 3 over 2. And I simply plugged them into my formula that we've got here. What do you notice about this formula here? When I look at it, I think that's very complicated looking. Whereas if we go back and look at the cosine function, the cosine on the previous, while the numbers are big, just a very basic calculator would allow us to calculate that number out. I'm not saying it would be easy, but we could calculate that out. Whereas the sine with this one centered at pi over 6 is a little bit more challenging to try to look at and try to actually evaluate. So this one would not be as useful to us because it's not something that we could easily calculate paper and pencil or on a basic calculator. But nonetheless, it can be done. Okay, finally, I'd like for you to look at a fourth maclaurin polynomial to approximate the value of ln of 1.1. So let's think about this. Now, notice that we're given less information here. First of all, it's fourth, so we're going to need 4 derivatives. We're going to need a function and then 4 derivatives after that. So I'm going to write those out. And then after that, we're also going to need to know where are we centering this thing at. We were not told where to center this at. Well, we're asked something about 1.1. We need a value close to it and something that we know the value of. So if you think for a moment, that's centered at 1. Excuse me for my poor writing here. Centered at 1. That will work out for us. So that's what we'll do is do a fourth maclaurin polynomial to approximate ln of 1.1 centered at 1. Okay, we've already gone through this, so some of you may have said, I'll just copy down what I did before, and that's fine to do. I'm going to work through it just so it's a little bit refreshing of our memory here. We've going through the process. Sometimes just the practice helps. So you've got these derivatives here. We want to know the value at x equals 1. So the first one is 0. The next one's 1, negative 1, negative 2, and then positive 6. I actually wrote that wrong down there. That will be a positive 6 over x to the 4th. So then our polynomial of degree 4 is going to be the function value at 1 plus the first derivative times x minus 1 plus the second derivative over 2 factorial times x minus 1 squared plus the third derivative, which actually I had messed up right here, hadn't I? That should be a positive, and this should go back to being a negative. I believe if we look back, I'm going to verify that. Yes, negative, positive, negative. So my mistake there. It is it's a negative, so 1 times x minus 1, a negative 1 over 2 factorial times x minus 1 squared, plus a 2 over 3 factorial times x minus 1 cubed, minus 6 over 4 factorial times x minus 1 to the 4th. That's our polynomial. And if you'll go back and look, it agrees with what we had written before, minus plus minus, and our numbers there. And now, how do we approximate the value of 1.1? You're simply going to put in 1.1 in place of x everywhere and calculate that out. So if you do that on your calculator, I think what I'd ask you to do is do the polynomial on the calculator, putting 1.1 in for x, see what you get, then use your calculator to do 1.1 and see what you get. And you see here, I've calculated those two. The first one is the natural log, using the natural log button on my calculator. And then the second one is actually putting in 0.1 into the polynomial that I got. And you see that we agreed for, actually I left it off there, 0.095. 1, 2, 3, 4, 5. Looks like for about 4 decimal places we did agree on those. So that's pretty good. So I hope that helps you to understand what we're doing here. I'm going to stop right here. You have a web assign that's due tomorrow night. It's 5 problems, very similar to what we've done here. And on Wednesday we will pick up and talk about remainder and the rest of this lesson, and maybe delve into power series a little bit. So go ahead and get started on that web assign. At the present time, you don't have any FRQs for this week. We will pick that project back up at a later time. So please go ahead and get started, and if you have any questions, feel free to email me.